Now what we're going to be talking about is we're going to be talking about a collection of charge moving in a magnetic field. And if you recall to a couple chapters ago, we defined a current as a collection of charge that is moving. Okay? Therefore, since it's moving, that collection of charge is going to experience a magnetic force when it is in the presence of a magnetic field. And so what we have, let's describe the picture a little bit. The picture we have is we're going to have a collection of magnetic field lines. We're going to have then a wire that's going to have a particular length L. So the length of the wire is going to be L. And it's going to move at a particular angle, theta, to the magnetic field. So theta is going to be the angle between the wire, not necessarily a wire, I should say a collection of charge, a movement of charge, a current. So that angle is going to be the angle between the collection of charge that's moving and the magnetic field. If we do a right-hand rule, you can imagine this collection of charge pointing out toward you, coming towards you. If you do the right-hand rule, remember your fingers are going to be in the direction of the B field of the magnetic field. Your thumb is going to be in the direction of the current, and your palm in this case happens to be pointed up, and that's going to be in the direction of the magnetic force F sub B. F sub B. All right? And that's what we have here. That's the picture that you see right here. Now, if we want to look at some math here, if we want to get into a little bit of math we can see that F is going to be the force of that magnetic field. That's going to be equal to Q, so that would be the charge. V is going to be the velocity in which the charges are being moved. B is going to be the magnitude of B is going to be the magnitude of the magnetic field. Now go back and recall that current, that what current is its charge per time. So if we take this, if we take the equation that you see up on top, all right, so up on top we see F is equal to QVB sine theta. We take the right-hand side and we're going to multiply that by 1. But the one we're going to choose is we're going to choose delta T upon delta T. That's really 1, all right? And then we're going to have a velocity times the B field, the magnitude of the B field, sine of theta. Now, if you recall, this term, Q over T, is equal to I. Q over T is equal to I. If you take a velocity times a time, that's going to equal a length. So it will equal a length. So once again, I is going to be the current, and L is going to be the length of charge that you have. And we can write this force now is equal to I, L, B, sine of theta. This is a much easier equation to deal with because it's very difficult to know the charge, right? It's going to be really difficult to know the velocity of that charge in which it's moving. But it's very easy to measure the length of that charge. If it happens to be a wire, we can just simply measure the length of the wire. So this isn't going to be all that too difficult to measure in a lab. We can measure the current. We can get an ammeter and measure the current. We can also measure the length with whatever instrument we need to do to measure length, and we should be able to measure the B field with an instrument. All right? If you have any questions, please let me know.